And the last talk of the session is on the black box complexity of private key inner product functional encryption by Mohammad Ajabadi, Roman Langreer, Adam O'Neill, Mingwan Wang, and Roman is going to give the talk.
Okay, thanks for the introduction. So first of all, a clarification, this is an entire classical result, so we don't do anything with quantum here. I want to start with a brief recap of what functional encryption is. So in functional encryption, we have a key generator here at the top, which generates a master public key and a master secret key, or in the secret key setting, just a master secret key. And it can also generate functional secret keys for functions f. And then the encryptor can encrypt a message m using the master public key, or in the secret key setting, the master secret key. And the decryptor can decrypt that key with his functional secret key, and then he obtains f of m. And security, informally speaking, says that an adversary that can obtain several functional secret keys can only learn about an encrypted message what it can learn by decrypting with his functional secret keys. And most works about functional encryption consider public key functional encryption, but some applications actually only require secret key functional encryption. So consider, for example, a user that wants to store some sensitive data m in the cloud, and the cloud now wants to compute f of m to perform some operation, but f of m actually is not sensitive. Then the user can just send the functional secret key for f to the cloud, and the cloud can compute f of m on its own. And in this setting, there's no need for public key FE. Secret key FE is completely sufficient. So a natural question now is if secret key FE is actually easier to build than public key FE, and what are the minimal assumptions that are required for secret key FE. And we know some things about this. So for example, in the bounded collusion setting, it is known that public key FE is equivalent to regular public key encryption and secret key FE to just secret key encryption. So here it actually becomes easier to build secret key FE. However, in the unbounded collusion setting, and the rest of the talk will be just about unbounded collusion, it is known that secret key FE and public key FE are equivalent, because actually both are equivalent to I/O. So here it doesn't become easier when we switch to the secret key setting. And such secret key to public key results are also known for other strong encryption schemes like additively homomorphic encryption and to some extent also circular secure encryption. However, no such result is known for FE for specific functionality. So when you focus on a simple functionality, it's not known if the secret key version implies the public key version. And this is what we want to investigate. And before we dive into inner product functional encryption, I want to talk about FE for point function, which is usually studied under the name of identity-based encryption. So in identity-based encryption, in the public key setting, we have many constructions, for example, from pairings, lattices, and many more. And we also have some black box separations. For example, it's known that it's not possible to get it from generic groups or from trapdoor permutation if you use them in a black box way. And once you go to the secret key setting, so secret key IBE hasn't been studied explicitly, but the reason for this is probably that it's trivial to build it from just one-way functions. So here it becomes easier when we go to the secret key setting. And now we want to answer if that also happens for inner product functional encryption. So in inner product functional encryption, the functionality or messages are vectors, functions are described by vectors, and the functionality is that you get the inner product. And again, in the public key setting, this is a very well-studied class of functions for FE, and we have constructions from groups, lattices, and class groups. And in the secret key setting, well, of course, we can use any public key IPFE, but there are also some works that explicitly construct secret key IPFE. But they aim to achieve function hiding, which is an additional security property, and that seems to make it even more challenging, namely this is only known from pairings. And yeah, so we want to ask whether we can get secret key IPFE from weaker assumptions like one-way function, as we have seen for IBE that was possible. And we show a negative result, namely we show that it's not possible to get it from one-way functions if you only use them in a black box way. And there are several oracle separations in the realm of functional encryption. I've already mentioned the ones for IBE, but there are also some that show predicate encryption for certain classes of predicates is not possible from trapdoor permutations or even IBE. And one idea that appears in all of these oracle separations is that it's impossible to compress an exponential number of public keys into a master public key that has just a polynomial size description. However, in the secret key setting, this is actually possible, because when you can generate an exponential number of secret key with a PRF, and then the PRF key is a succinct description of that. That's also the reason why secret key IBE becomes trivial from one-way functions. And this shows that the idea of all of these oracle separations doesn't carry over to the secret key setting. And moreover, all of these oracle separations are only for predicate encryption, and IPFE doesn't fall under this class. So this is why we have to develop new techniques to show our separation. So what we actually show is that there exists no unbounded collusion secret key IPFE in the random oracle model. And that means that should be secure against adversaries that have unbounded time, but can make only polynomially many random oracle queries. And as shown by Impagliazzo and Rudisch in their pioneering work, when we have such a result that implies that there exists no unbounded collusion secret key IPFE from any primitive like one-way functions or collision-resistant hash functions, if it only uses them in a black box way. Okay, now I want to talk a bit about the security proof. So very informally, in our security game, the adversary tries to predict the inner product between a vector v star that he knows and a random vector w, and he is given a ciphertext for w and many functional secret keys for vectors vi, and we need this condition here that v star is not in the span of these vi's, otherwise he can win trivially. And then on a high level, what we do in our attack is that our adversary makes a brute force search for the functional secret key for v star, and with each candidate key, it tries to decrypt the challenge ciphertext. And our actual security game is a bit more complicated and allows the adversary to check if a solution was correct or not. Now, making that brute force search is fine because our adversary is unbounded. The only problem is that decryption can make random oracle queries. And so we have to simulate these random oracle queries ourselves without querying the real random oracle. And the important part here is that we do this consistently. So we have to answer the random oracle queries that appear during key generation or encryption and also decryption in the same way. So we do this by learning these intersection queries that are shown here in red in the beginning. And we ignore the intersection queries with key generation here because this can be solved with standard techniques. The interesting part is how we learn the intersection queries between encryption and decryption. And well, the strategy of our adversary is that the adversary decrypts the challenge ciphertext with all the functional secret keys that he got and observes the random oracle queries that appear there. And now we need to show that the random oracle queries that he has learned, they're shown here in green, they contain this intersection that we want to learn. And we formulate this property that we need here as a problem of extremal combinatorics. Namely, we formulate we abstract it in the following lemma. So the lemma says that for every function f that maps our vectors to a polynomial size set, and the intuition here is that this polynomial size set describes the random oracle queries that were made during encryption, and f of y now are the random oracle queries that also appear when we decrypt with a functional secret key for y. So what's shown here in red. And then the lemma says, okay, that f of y star is with high probability a subset of all of these f of yi's, the union of all of these f of yi's, if we choose our vectors uniformly at random, conditioned on this y star is not in the span of y1 to yt. By the way, without this condition, this would be trivial, because then y star and all of these yi's are from the same distribution, and this becomes a very simple argument. But because of this condition, they are actually from disjoint distribution, and that's what makes it challenging. And we prove this. First, we prove a VK variant that only shows the existence of these vectors for q equal to 2, based on the double counting technique as a warm-up. Then we strengthen that result to the variant that we actually need for our result using Fourier analysis. And finally, we generalize it to arbitrary primes q using a combinatorial technique based on the Cauchy-Schwarz inequality. So to summarize, we have seen that secret key IPFE, despite looking like a secret key primitive at first glance, probably requires public key assumptions. And this is in contrast to other functional encryption schemes like secret key IBE. And it would be very interesting to get a better understanding of what the black box complexity of other functional encryption schemes is. So for example, for a secret key attribute-based encryption, we don't know whether it can be built from just one-way functions or not. And even for secret key fuzzy IBE, which is a very simple variant of attribute-based encryption that's just a bit more general than IBE, we don't know whether it belongs to the minicrypt world, where we can get it from just one-way functions, or whether we need public key assumptions. Thank you.
Any questions for Roman?
Is it known, well, I mean, I assume not, but some cause intuition says that secret key IPFE might imply, let's say, regular PKE. This is not known?
No.
And is there separation or?
I also don't know for separation, but yeah, I think it's not known.
And maybe a related question in orthogonal direction, but like, so you said Zandri separated IBE from even generic groups, right?
Yeah.
So can you separate secret key IPFE from generic groups, or is it?
No, because public key IPFE can be built from generic groups, and thus also secret key IPFE.
Oh, I see. So nice. I didn't. I missed that. Cool.
Yeah. So once you have generic group, it's possible just from one-way function. You can't get it.
Cool.
Another quick question. All right, then let's thank Roman again and all the speakers of the session.